right. So today I want to talk about function fields. And in the previous version of this course, in the seminar that I ran, I think some people had difficulty to understand this subject. So I hope to give a better explanation today. And let me first start with the motivation. I mean, recall that we want to think of Kx, where K is a field, as analogous to the integers, right? We can factor a polynomial to prime components, and we have GCD and so on. This analogy is actually even stronger, even deeper when K is finite, which is many times what we're interested in. But for now, let's try to push. So to push the analogy, we can imitate the construction of Q the rational numbers from the integers. How do we construct Q from the integers? We say we define an equivalence relation on set of integers. Sorry. Define an equivalence relation on the set of integers whose second coordinate is non-zero. And we say that AB is equivalent to CD, and this AB represents the equivalence class of AB would represent what we want to think of as A modulo B, or A divided by B. And this, of course, would be C divided by D. So we want to say that they are equivalent if and only if AD is equal to CB. Okay? And it's very easy to check that this is an equivalence relation. So Q, in the fundamental mathematical definition, it's simply the set of integers whose second coordinate is non-zero modulo this equivalence relation. Okay, so this is and the equivalence class of AB, as I said, is denoted as A divided by B. Okay, so how do we do it for polynomials? the function field in one variable is simply the quotient of polynomials, or the Cartesian product of polynomials in X times itself, but such that the second coordinate is not the zero polynomial, modulo the equivalence relation that you can guess, f g is equivalent to f prime g prime, or maybe h I, if and only if f times I is equal to h times g. Okay, and we denote, so in other words, the function field in one variable is simply the set of quotients f divided by g, such that f and g are polynomials in one variable over k, and g is non-zero. And of course, the implicit relation is the one coming from the equivalence relation here. Okay, and this is a field, right? Because I mean, addition and multiplication is just like from fractions. I mean, from Q, and it's going to be associative and distributive and so on. And the multiplicative inverse of a non-zero element, f modulo g, is going to be g divided by f. Okay, is this? Are there any questions on this? Now, maybe let's remark on the one variable case. We saw that k brackets x is the minimal field containing k and a new symbol x, right? Because any field that contains k and the symbol x, it must contain all polynomials in x. And since it's supposed to be a field, it must contain all the inverses of polynomials, so 1 divided by a polynomial in x, and we get the function field. Now, when we do elliptic curves, we want the two variable version. So that's not hard. We define k xy to be the set of all quotients f xy divided by gxy, such that f and g are polynomials in two variables over k, and g is non-zero. And this is again the field, the function field, or also it's called the field of rational functions. Now, why should we care about rational functions in two variables? Well, if we have an elliptic curve over k and a rational point, I mean a point on E of k, then we defined the doubling of the point. The doubling of the point, it had some formulas which I will not repeat because first I don't remember, and second it's not relevant, but it is some pair of rational functions. Where R and R prime are rational functions in two variables. Right? And I cannot, it's not just R and R prime are not simply polynomials, because when we define, for example, the tangent line, we divide by a polynomial. I mean, we took the derivative. We have some rational function, not just a polynomial. So if we want to, for example, understand this doubling of the point when p varies, then we need to understand rational functions in two variables. Now, we call it rational functions, but it's not actually functions. So every element R let's say it has a representation f modulo g. Or let me even just pick a specific representation, f modulo g. It defines a partial function this partial function is from the affine plane A2 into K. And this goes as you take a point, x node, y node, and you send it to f of x node, y node, g x node, y node. But of course, this is a partial function, because when x node, y node nullifies g, or when it is a root of g, then this function is not defined. So this is not defined. It's not defined on the curve CG, which is the set of solutions to the equation gxy equals 0. But there is a subtlety here. So this representation is not unique, right? And it could be that I take a different representation. Let's say if f modulo g is equivalent to f prime modulo g prime, and this of course means that f times g prime minus f prime g is equal to 0, to the 0 polynomial. Then it could be that I mean the set of roots of g is different than the set of roots of g prime. So you know, on one representation, this would define a partial function defined on a certain subset of the affine plane, and on another representation, it will be a partial function defined on another subset of the affine plane. For example, we can consider the two functions, two rational functions, x squared times, modulo xy, and xy modulo y squared. These are two rational functions in kxy. And they are equivalent. I mean, they are equal in kxy. But of course, you know, one of them is not defined on the line x equals 0, and the other is not defined on the line y equals 0. So we have a different domain of definition. We will say that a rational function r xy is regular at P if there exists a representation Rxy equals Fxy modulo Gxy, such that G of P is non-zero. Okay, so this is rational functions in two variables. So on the affine plane, you can view rational functions in one variable as partial functions on the affine line. But what we really want to look at is rational functions on elliptic curves. So now Yeah.
I'm sorry, could you remind what is a partial function?
Partial function is simply it's something that is defined, or I mean, it is a function that is defined on a subset of the domain. It is not defined on all the points.
Okay, okay.
Okay, so in our case, I mean, it is not defined on any time that is. I mean, any time that you have a point that is. I mean, if R is not regular at P, then you cannot define the resulting function at P. I mean, maybe I should add to the previous definition. In this case, we define the value of R at P as simply FP modulo GP for the specific representation the appropriate representation. Okay, and you can see it's very easy to see that if in one representation G of P does not vanish, then in any other representation such that the denominator is does not vanish in P, you get the same value. You get, I mean, if you substitute P in the other representation, you will get the same value as FP modulo GP. This is simply because of how we defined the equivalence relation on the set of I mean, rational functions. Yeah.
Maybe I'm messing up different things, but is it like when we say that P is regular, is it this R is regular as P? Is it the same that before we called like well-defined at P?
You could say well-defined is a general term in mathematics that refers to cases where you're trying to define something on representatives, but you want to claim that your definition actually does not depend on the choice of representatives.
Oh, I see.
This is generally so. It's related. I mean, but in algebraic geometry, this case is called regular. I mean, regular is some generic terms that is used all over mathematics when you want to say that something is nice. There are like regular, normal, and so on. So this is just a standard terminology.
And so in this case, it will mean regular will mean that it is defined in this particular point P.
Yes. Again, but what is defined in a particular point? It means that there is a representation for which it is well. I mean, for which the denominator does not vanish at P. Of course, you can always multiply. I can always multiply this representation by say x minus y, or whatever. I can multiply this representation by a polynomial that does vanish at xy, and then it would not be defined, right? So just like in this example here, right? I can always multiply by whatever I want. I mean, say y and so on. So what I'm looking for is rational functions that are that admit a representation that is defined at P. Okay? So now let E over K be an elliptic curve. With, let's say, the defining equation, I call it phi xy. So E is phi xy is just say y squared minus x cubed minus ax minus b, and E is the set of solutions of this polynomial, and for any finite point P in the k rational points. Finite, I mean simply not the point at infinity. We can consider any rational function well, any finite point, we can consider it as a point in the affine plane, right? So we can consider any rational function say f modulo g say with the variables as restricted to the finite points, right? So to ek minus the point at infinity. This is of course a subset of the affine plane. Now note that if phi divides the polynomial gxy, then this rational function R is not defined on any point in the elliptic curve minus the point at infinity, right? This so this is kind of a very bad case we want to avoid. So otherwise, yes.
Sorry, I'm not sure I understand why it is not defined.
Because any point on any rational point on E would satisfy phi xy equal 0.
Oh, yes. Okay. So if it's a multiple, yeah. Okay. Thanks.
Okay. So again, this we need to be careful with this notion of division. I mean, there is a notion of division of polynomials into variable. It's just that we don't have all the toolkit of GCD and so on. But we can still talk about two polynomials in two variables that divide each other. For example, x minus y divides x minus y times x plus y. Okay, so this is completely, I mean, completely legit to talk about, but we need to be a bit careful. So if he divides the denominator g, then we don't get anything interesting on the rational points of E. And in the rest of the cases, so otherwise, if phi does not divide G, then we could, so f xy g xy is defined on all points x node y node such that the ones that satisfy g x node y node is non-zero. And as a remark, how many points can there be such that gx node y node is non-zero? Remember, these need to be points in E of k. So it is really an intersection of two curves. And there is a theorem that two curves can intersect at most in the multiplication of their degrees. So the number, this is like a generalization of the phenomena that we saw, that the tangent line can intersect a cubic at most at 3 points. This is because the tangent line is a degree 1 curve, and the cubic is a degree 3 curve. So they can intersect at most in 1 times 3, that is 3 points. And in the more general case, this is called Bezout. The intersection of E with the curve CG is at most degree phi, the defining polynomial of E, times the degree of G. Okay, but we don't rely on it. This is it's quite involved to prove it, but we don't need it. But it's nice to know that we have some kind of bound on how many bad points this rational function can have. So we will call a rational function f modulo g in kxy such that phi does not divide G, a rational function on E. Okay, and we can define equivalence relation on such functions by fxy modulo gxy is equal to f prime xy modulo g prime xy if and only if, or I should say equivalent, if and only if, now instead of saying fg prime minus f prime g is equal to 0, I want to say that it's equal to 0 modulo phi. So phi divides this polynomial. Okay, this is basically what I'm doing here is recall that when I had polynomials in one variable and I had a polynomial phi, it didn't have to be a prime polynomial. This was a mod phi arithmetic. Right? It means that f is equivalent to g if and only if f minus g, instead of being equal to 0, it's equal to 0 modulo phi, which is, again, it's the same as saying that phi divides f minus g. And what I'm doing here is the same in two variables. Okay, so I'm considering the mod phi arithmetic on polynomials in two variables. So in other words, the field of, I mean, the set of rational functions on E with this equivalence relation is in notations, it is kxy modulo phi, which means, right, that it's also the same as well, the equivalence relation, as I said, is this. Okay, so this is all to motivate the following definition. For an elliptic curve E over K, the polynomials over E, or maybe on E, is the set KE, which is simply KXY modulo this defining polynomial phi. Okay, so this is kxy modulo y square minus x cube minus ax minus b equals 0. All right, so by definition, in E of k, sorry, I miswrote. This should be k of e. Okay, this is like polynomials on e is k of e. And in k of e, we can replace every. I mean, we can look at it as just ordinary polynomials in two variables, and whenever we have a term that is y squared, we can simply replace it by x cubed plus ax plus b. So if f is a polynomial in k of e, we can replace any term y squared with x cubed plus ax plus b. And this means that fxy can be written in what is called a canonical form, that is what notations do I choose? Say Vx plus y wx for some pair of polynomials v and w in one variable, right? Polynomials in x. Because I replace all the terms y square. Potentially, I mean, I have a term y that I cannot replace. I mean, if I had square root, I would be able to replace y with the square root of x cubed plus ax plus b, but in general, I don't have it, so I keep it as is. And I get that fxy is equal in ke, right? This equality is in ke, is not an equality of general polynomials in two variables, but in k of e, I can write fxy like this. Okay, so I claim that the canonical form is unique. I mean, you cannot write it in two different canonical forms. Before the proof, are there any questions on this?
No.
Okay, so it's very straightforward. I mean, you could have done it as an exercise, but just to to give you a sense, I mean, fxy, say it's equal to vx plus ywx, and let's say it's also equal to v prime x plus yw prime x. Then I can do just reorganization and get that vx minus v prime x plus y wx minus w prime x is equal to 0. So I call this this one new. I call this one omega. It is enough to show that nu x plus y omega x equals 0 implies nu x equals 0 and omega x equals 0. Right? This would equate v and v prime, and also w and w prime. So how do I show that? 0 is, of course, 0 times nu x plus y omega x. And now I do a trick that we will see. I mean, you see in many such situations, like in complex numbers, I simply multiply by the conjugate. So wait, hang on. I want this one. Right? 0 times anything is 0, so I take it to be the conjugate, but now I can replace this 0 with nu x plus y omega x, and I leave the second one as before. This is nu x minus y omega x, and this is nu square x minus y square omega x, omega square x, which again is like I can replace the y square. So this is nu square x. Let's say plus minus sx omega square x, where sx is x cubed plus ax plus b. But the degree of S is odd. and the degree of nu square and w square, omega square, are even. So the only way this could happen is that omega needs to be the zero polynomial, and hence also nu is the zero polynomial. Okay, and since we used this conjugate, let me just make it a definition. Let f in K of E be given in canonical form as f xy equals vx plus y wx. The conjugate of f is f bar, which is simply vx minus y wx. Okay, and the norm of f is simply f times the conjugate. This is analogous to what you have in complex numbers. I mean, in C, you have you take a complex number, you multiply it by the conjugate, you get what is called the L2 norm of the complex numbers. Okay, and so f times f bar, this is going to be a v square x minus y square w square x. And as we did in the proof, I can replace the y square by s of x. So this is v square x minus x cubed plus ax plus b w square x. Okay, and this is in K of E. All right, we're getting close to a break, but any questions or remarks?
Maybe a question about degree check, where you told that the degree of Sx is odd, but
Yeah.
the degree of Vx of mu and omega is even.
Mm-hmm.
But in fact, if you multiply the degree of the odd degree of Sx and the even degree of omega x, you will get even degree. And mu also have even degree.
Right, let me think. So we have, yeah, I would get, this is odd. Yeah, there is an issue here. I mean, one thing is that the degree of V would be of new. Let me check. Yeah, let me. I would need to think about it. Actually, it's a good catch. Yeah. Other questions? Okay, so let's take a 10 minutes break, right?
Sure. See you now.
Okay. Can we start again?
Yeah, there has been a discussion in the comments, Matan, about the topic of the degrees. So maybe we want to revisit it.
Okay. Yeah. Yeah. Thomas, that's exactly right. That is what I missed. So the proof is valid. Right? Just let me repeat. I mean, this is even. This is odd. And this is even. Then the degree of the multiplication of polynomials is the sum. And the sum of odd and even is odd. So this is a contradiction. Okay. Is this clear? Just to
Yeah. One more question, Matan.
Yeah.
Just to like have a broader picture, like where is this like going towards, or like how does this fit in with like the previous classes that we've had, like this topic specifically? Maybe I missed it because I was not in the first 5 minutes.
Yeah. Well, we want to understand this, generally speaking, to understand a algebra geometric object like an elliptic curve. We want to understand functions on it. Okay. So the natural notion of I mean, functions, of course, for us, this is all like algebraic functions, polynomials. But polynomials on E is this notion that we defined, K of E, that is a bit more involved than just ordinary polynomials. And what we will do eventually, I mean, I will soon define rational functions on E. Again, in the same vein that we defined rational functions on the affine line, right? As kind of an imitation of the construction of the rational numbers. And rational functions on E will be crucial to construct the pairings. Okay. So this would be. But if you want a simpler motivation, then remember that when you double a point, I mean the general function of doubling a point. Forgot where it is, but yeah, here. The general function of doubling a point on E is a pair of rational functions, right?
Yep.
And so if we want to understand the doubling of a point from a more profound way, whatever, we want to understand rational functions.
Fair enough. Thank you very much, Matan.
I'm sorry, can I double on that question? You mentioned that we're gonna look at rational function on E, but I thought it was already R of X and Y, the rational function on E. Didn't we already define this? I thought R was.
We didn't define explicitly. It's true that, okay, or depending on how you treat it, but I want to define it in formulas.
Okay.
Okay. So maybe this is actually the next thing. Of course. Okay, so maybe remark. So we have a K of E is this Kxy modulo this polynomial phi. And it can be shown that phi is irreducible. I.e., we cannot write, or it cannot be written as phi equals A times B for non-constant polynomials A and B in two variables. So this is what we called, in one variable, we called it prime. But the proper term for a multivariable polynomials is irreducible. And remember that when we took the ring of polynomials in one variable and we divided by a prime polynomial, we got a field. Okay, but the proof that this was a field relied on the fact that we could do GCD. And in two variables, we don't have a well-defined GCD. So K of E is not a field. Right, and you can find example. I think I wrote in the notes. There are examples that show you that you have a. I mean, it cannot be a field because you have zero divisors, or you don't have multiplicative inverse for let's say, e.g., x has no multiplicative inverse. Okay, so the two variable case is more involved, but nevertheless, we want to turn K of E to a field in kind of a minimal way, right? This is the whole theme of this rational, field of rational functions is to extend K with some additional variables to the minimal field that contains both. So the way to do it is, again, to imitate the construction of the rational numbers. And this is the following definition. For E over K, an elliptic curve. The set rational functions on E is, I take polynomials on E times polynomials on E that are non-zero. Non-zero, again, non-zero as polynomials in E, right? And I divide by an equivalence relation, which is, as you expect, f comma g is equivalent to f prime comma g prime. if and only if f g prime minus f prime g is equal to 0 in K of E. Right? So basically in K of E, it means that if this expression is equal to 0 if and only if phi divides, let's say this is equal to t times phi for some t. Okay, so this we are you have layers of equivalence relations, right? But this is I hope that I could convince you that this is a natural chain of definitions to make. Now, to check if this, of course, this f comma g, we will denote it as f divided by g. So to check if f modulo g is equal to f prime modulo g prime, we can put f times g prime and f prime times g in canonical form. And then it's just polynomials in one variable. I mean, plus this y times a polynomial in one variable, and we can simply compare coefficients. All right. So this is a practical way to see if two rational functions on E are equal. Yes.
Yeah, sorry, Matan, I got a bit lost in this last thing. So you started giving a definition that you can, if I understood correctly, count the exact amount of rational functions on E?
Say again? Yeah, I can.
Like, what you're stating that you can count the exact amount of rational functions on E?
No.
Okay. So, sorry, can you then repeat what the definition is stating? Because I got lost.
So the definition is this one, k round brackets E. This is analogous to the process we had, right? That we had in the kind of affine case.
Sure.
I mean, we first we define a notion of polynomial, and then we define the field of rational functions as a quotient of polynomials such that the denominator is non-zero. Right? Or alternatively, it's like a set of pairs, a modulus some equivalence relation. This specifically this equivalence relation.
Mm-hmm.
Right? So now that I have the notion of polynomials on E, right? Polynomials on E is what I would naturally consider as polynomials restricted to the elliptic curve E. Right? It's like polynomials in two variables modulo the defining polynomial of E.
Sure.
Okay, so now I just continue with kind of the same recipe that I have. I have rational functions on E is simply, I mean, alternatively, you could simply define it as the set of all f modulo g such that f and g are polynomials in E, on E, and G is non-zero. But again, non-zero means non-zero as a polynomial in K of E. Right?
Okay.
So
Yeah.
remember that in K of E, for example, the polynomial phi is zero.
Mhm.
Right? So what I need is to say that G is non-zero is essentially saying that that phi does not divide G.
Okay.
So
Okay.
I could even write it like this: f modulo G such that fg are polynomials over E, and phi does not divide G.
Okay.
Okay, but this again, there are kind of layers of equivalence relations because of the I mean, because of how we defined it. We want a notion of polynomials over, I mean, polynomials on E. This is not just ordinary polynomials, it's like polynomials with the if you want, polynomials on E is like polynomials in two variables in which you can replace every term y squared by the term x cubed plus ax plus b. That's polynomials on E.
Does this imply any sort of linear dependence relation or something like that, or
Between what?
between the polynomials that you define in this set and the primitive polynomial that defines that would be the curve equation, to put it on some sense, or that defines the curve?
I'm not sure I understand the question entirely, but it does not need to be linear relation in any case.
Okay.
We simply have, I mean, the defining equation of the elliptic curve give you a relation,
Sure.
right? Y squared equals x cubed plus ax plus b.
Yeah.
And you say that a polynomial in two variable is a polynomial on E once you can replace all the terms y squared by their equivalent I mean by x cubed plus ax plus b. And this is called polynomials on E because you can only do it for points in E. Points on E satisfy this relation.
Fair enough. I see now. I see. This is the bit that I was missing. Okay, fair enough. That
Okay?
makes sense. Yeah.
And once I have a notion of polynomials over E, I naturally define rational functions over E as this Q construction, basically.
Mhm.
Okay.
Okay. Yep.
And of course, K of E is a field with the natural addition and multiplication that you want, and the inverse. I mean, the multiplicative inverse is again as we had in the previous cases. Okay.
Yep.
Now, yeah.
Sorry, Matan, one more question. Have you proven that this is actually a field? In the sense of, how do we know that every polynomial, I mean, I don't even know if you can say that they have an inverse, but a field implies that every element inside of it has a valid inverse. So
Yeah.
is this already like implicit or proven somewhere, or we are just gonna skip it and that's
I can prove it if you want, but I think it's actually a very good exercise in the definitions.
okay, fair enough.
To prove it. But how do you do it? I mean, you have addition and multiplication defined. For example, how do you define multiplication? You simply say that this is the f times f prime modulo g times g prime. Right?
Yeah.
In addition, you define similarly, just like you know from addition of fractions.
Sure.
And what will be the inverse of f modulo g? I mean, the inverse, remember, in a field, we only require that non-zero elements have multiplicative inverse,
Okay, I see. Fair
right?
enough.
So
Yeah.
this is, if this is a non-zero element, it means that not only g is non-zero, but also f is non-zero.
Yeah.
So the inverse is simply g modulo f.
Okay, fair enough.
Okay. So we naturally get a field. This is the field of rational functions on E.
Thank you. Thank you.
As another remark, remember we had canonical forms for polynomials in polynomials on E. But we can do canonical forms for rational functions on E. So for let's say R equals f over g in rational functions over E, I can write f divided by g, and now I do the conjugate trick. So I multiply and divide by g conjugate. And this is equal to something in the numerator divided by the norm of g, right? G times g conjugate is the norm of g. We write the numerator f g conjugate in canonical form. So let's say f g conjugate is xy is a vx plus y wx. And remember, the norm of g is a polynomial only in x, right? We had it. You see that the norm of g is, I mean, I have y square over there, and I can simply plug in this sx instead of y square. So this is a, let's say, v prime x minus s of x w prime, sorry, this is v, let's say, new square of x and omega square of x. So this is a polynomial in x. Just a minute. It means that I can write f over g as vx plus y wx divided by some polynomial in x. So this is new square x minus sx omega square of x. And this is simply some rational function in x plus y times some other rational function in x. Okay, so this is and this is in the canonical form of R. Yes.
You use the term norm as the definition of a size of a vector space or something like this, like as in geometry, or
It's by analogy. I mean, the term norm, we defined it as just you take G, you take it in canonical form. So this is some Vx plus YWx. And then you have the conjugate of G. This is Vx minus YWx. And the norm of G is simply defined as G times G conjugate.
okay, fair enough.
Okay, and we saw that you can, I mean, you can manipulate the symbols to get this formula.
Does there's any like underlying similarity between how we understand the norm here and how you understand the norm for like vectors and planes and stuff like that?
It's just by analogy.
Okay, fair enough.
Yeah,
Fair enough.
it's not meant to be like a very deep analogy. So okay, it's just a term for us. But if you open the formula, you find out that the norm of G, I mean, G is a rational function on E. Sorry, G is a polynomial on E. So typically it is something in two variables. You have X and Y, but what we did, the manipulation of the formula showed that when you take the norm of G, that is simply G times G conjugate, you can turn it into a polynomial in only one variable.
Okay, fair enough.
Right?
Okay,
Because
okay.
this Sx
Yeah.
replaces Y square. So using this fact that the norm of G is a polynomial in one variable, I can turn a rational function f over G. This, I guess, I mean, to be more precise, I should write fxy divided by gxy. I can turn it into a rational function only in x plus y times another rational function only in x. And this is analogous to the canonical form of a polynomial on E. Okay?
That makes sense. Thank you very much.
And maybe, okay, exercise. The canonical form of a rational function of R in the field of rational functions over E is unique. Okay? This again, it will be a good exercise to simply revise the proof of uniqueness in the case of polynomials over E and do something similar. Yes.
Sorry, I'm going to ask a question that so something you did on the first hours. How can we get only a y term in the canonical form if the elliptic curve equation contains a y square?
Because we take a polynomial, I mean, let's say you take fxy, a polynomial in two variable over k, right? And now, if you want, you can define the modulo map from kxy to k of e. Polynomials over e, this k of e, are simply defined as kxy modulo phi. Phi is the defining polynomial of e. So phi xy is y squared minus x cubed minus ax minus b. Okay? So this map is simply taking f into or we can call it, I don't know, f. I mean, this is f modulo phi basically. Okay.
Yep.
But what does it mean to do the quotient ring? I mean, a kxy modulo phi. It means that in this quotient ring, y square is equal to, I mean, if phi is equal to 0, this means that y square is equal to x cubed plus ax plus b in this k of e.
Yep.
Okay, so the kind of the simple way to do the modulo phi I mean operation is I take all the terms in f in fxy that are y square or powers of y square. So all the even
Oh, I see.
yeah,
Okay.
and I replace them by x cubed plus ax plus b.
Okay, so yeah.
And then
The
I am left with some polynomial in x plus y times some other polynomial in x.
makes sense. Thanks. Okay.
Okay. So we have this we have this this perspective that a rational function can be defined on all the finite rational points of E. But we actually want it to be defined over all the rational points of E. That is, we want to make sense of what is R evaluated at the point at infinity. Now, to do this, we draw an analogy from calculus. So let me remind you. Let's say, so we think of maybe for a rational function R on the elliptic curve, what is R evaluated at the point at infinity? So, I mean, we will do rigorous definitions, but as an intuition, you can think of O as like infinity comma infinity. Okay, so it's as if O in the x coordinate has infinity, and in the y coordinate also infinity. Now, to make sense of the definition, I mean, to motivate it really, what do we do, let's say in one variable? What is, I have, let's say, a rational function, say x divided by x squared plus 1. And I want to evaluate it at infinity. I mean, of course, if I like on the nose substitute infinity, I get nothing. I mean, I get infinity divided by infinity. I cannot make sense of it. But in calculus, what you do is you look at the value of the function at a sequence of finite numbers that gets close to infinity. I mean, what is called tends to infinity, or a sequence of number whose limit is infinity. And then you define R at infinity as the limit of the results, I mean, of the value of the function on this sequence of finite numbers. Now, what you can do in simple terms is basically divide the numerator and the denominator by the highest degree monomial. So to see what is,
Are we doing L'Hopital or something similar?
it's kind of L'Hopital, yes. It's
Okay.
kind of L'Hopital. What is R at infinity is like the limit where x tends to infinity of this expression, x divided by x squared plus 1. And what we do is we divide by x squared both the numerator and denominator. So we have x squared divided by x squared plus 1 divided by x squared. And this is 1 over x divided by 1 plus 1 over x squared. And I should put limit everywhere. And now in the last expression, I can actually calculate it, because 1 divided by infinity is 0, and also 1 divided by infinity square is 0. So I get 0. I get 0 divided by 1 plus 0. This is 0. However, if I want to do the same thing for, let's say, R prime is x squared plus, divided by x squared plus 1, then R prime at infinity would be, again, the limit x tends to infinity, x squared divided by x squared plus 1. And this is x squared divided by x squared modulo x squared divided by x squared plus 1 over x squared. And this is actually 1 divided by 1 plus 0, so it's 1. And what I want you to take from these two examples is that I mean, we don't need the whole theory of calculus for limits and all that for all functions. I mean, sine and cosine and natural logarithm and stuff like this. We only care about polynomials, and for polynomials, you have a very simple rule. I mean, if the degree of the numerator is bigger than, okay, if the degree of the numerator is smaller than the degree of the denominator, then you get 0, like in the first example, right? The degree here is 1, the degree here is 2. And if you tend to infinity and you divide polynomial of degree 1 by polynomial of degree 2, you always get 0. I mean, this is not a proof, but I think you can understand it intuitively, right? Once I will divide by the highest degree monomial, I will always get 0 at the limit. On the other hand, if, well, of course, if the degree of the numerator was bigger than the degree of the denominator, then when I take tend x to infinity, I get infinity, right? It's like, it's kind of a stronger, a faster tendency to infinity of the numerator compared to the denominator. So I get infinity. And if the degree of the numerator and the denominator are equal, then I should expect that when I tend to infinity, I get some finite number. Okay, is this this intuition somewhat clear? All right, Carlos, is it?
Yeah. Oh, sorry, you're not seeing the screen. Yeah, everyone throw a thumbs up.
Okay.
So yeah, we all said yes. Yeah.
So yeah, so I mean, I just want you to feel comfortable in the, I mean, eventually we just make a formal definition. It's not not a formal matter, but rather just to motivate you. Okay, so what will we do in the so in K of E, we have a bit of a subtle situation. First, we want to define the degree. I mean, the notion of let's say degree of f for f in K of E, it needs to be adjusted because since we have a relation y squared equals x cubed plus ax plus b. So you know, y square in ordinary polynomials, the monomial y square would be of degree 2, and the right hand side would be a polynomial of degree 3. So how do we make sense of it? We said f x y in canonical form and again we have this relation y squared, so y squared equals x cubed and so on. So I want to say that the degree of the variable y will be, I mean, the relation between the degree of the variable y and the degree of the variable x will be 2/3, right? So the relation between the degree of x and the degree of y should be 2/3. But of course, it's more convenient to have degrees being integers. So we define the degree of y is equal to 2. And sorry, the degree of y equals to 3. And the degree of x is equal to 2. And hence, the degree of f is going to be the maximum between 2 times the degree of v. Remember, v is just a polynomial in x, so it has a well-defined notion of degree. And the second term is y times wx, but y is of degree 3. So this is 3 times 3 plus 2 times the degree of w. Okay, so this is our notion of the degree of a polynomial. I mean, a polynomial over E. All right, we ran out of time, so I suggest we stop here, and I mean, you can ask questions, but where we're heading, what we'll do next time is we use this this analogy from calculus and our new notion of degree to define what is R at the point at infinity.
Cool. I'll stop the recording.